Hello everyone, the problem that we're looking at today is the USACO 2025 February Silver Contest Problem 1 of the best lineup. So the contest is currently over and that is why I'm able to make this video. However, I did screenshot the problem and all the samples including the subtask, so that is why I'm still able to make this video right now. So you can pause the video first and look through the problem statement yourself and the samples. Okay, so basically, Farmer John has n cows and being at most 2 times 10 to the 5th power, and now you're trying to construct an array B using the array A given in the order of the cows, where B is initially empty, and as long as A is not empty, you remove the cow at the beginning of A and potentially add it to the back of B. So what does that mean is basically every time you take the head of the QA, and if you want to add it, you can add it to the back of B, or you don't have to, and then you try to get the lexicographically greatest B. And the definition of lexicographical order is defined in this problem as this. So the first position I, where SI is different than TI, if S is greater than T lexicographically, then SI must be greater than TI. However, if no such I exists, which means that S is a prefix of T or T is a prefix of S, then S is longer than T means S is lexicographically bigger. So basically, the lexicographically greater one is the longer one of the two sequence if one of them is a prefix of the other. And now you can look at the sample too. Basically, you have cows 4, 3, 2, 1, 3, and oh wait, forgot to mention, you can also make one operation before you actually start constructing T, and that operation is choosing the cow in line A and moving it anywhere before its current position. Notice it's before its current position. That is the important part. And then look at the samples. This 4, 3, 2, 1, 3 is the order of the cows, and then you can move cow 3 to between 2 and 3, and then you add every single cow in A into QB. And for the second test case, however, you can't get every single cow because the best you can do is to move 6 into the beginning of the line, and then you only add 6, 5, and 4. So now you can pause the video once again and think about how to do this problem yourself. Alright, so the first thing that I noticed for this problem is that what the problem is actually asking from us, if we first ignore the statement of doing an operation before constructing B, is basically for every A, we choose the suffix max of I. So for every I, let's say, we only choose this I if it's the suffix max, meaning it's bigger than any suffix starting from I. So say this I, it is the suffix max, then we definitely choose it, meaning put it at the back of B. However, this I, since this one is far bigger, we will not be choosing this I. Because think about it, if we did choose this and put it to the back of B, if in another sequence we chose this I, which is bigger, it's going to be lexicographically bigger, which is why we only choose I if it's a suffix max. However, we still haven't solved this problem because, well, we need an operation and we can't determine the best operation. Well, my first idea during the test is, well, to enumerate where to move each cow. And what I did was basically I realized that if you're moving a cow, you're definitely going to be moving it right behind the first cow greater than or equal to the current cow's label. And then I just found that position for every cow and then enumerated if we move every single cow and then what is the maximum number of suffix max we will get. However, that is incorrect because the maximum number of suffix max we will get is not necessarily the lexicographically greatest sequence. And you can think about why that is so yourself. And let's just go on to the real solution, the correct one. So my solution in this one is basically just greedy and simulation. Basically, obviously, you input test case and n, and then I put all the a values into an array called val, where val.first is the value of a, and .second is the initial position of a, which in this case is I. And then we sort val using a CMP sort function, which compares the actual value first. If the actual value is greater, we put it in the front. However, if the two numbers had the same value, we return the one that appeared the earlier. And after we sorted them, we just go through the list because we know that since the bigger values are sorted into the first of the sequence, if we go through them from 1 to n, the earlier the number came, the more we want them, right? So we want 1 the most and we want n the least. And how do we know if we can have this I? How do we know if we can actually add it to the end of B? Well, I kept track of an MA and an MA2, where MA is the maximum cow that you already chose, and MA2 is the second maximum cow you already chose, and that maximum is not the maximum value, but the maximum position. So MA is basically the latest position of any cow that's already been chosen from 1 to I minus 1. So what does that mean? Basically, this graph is a bit messy. Basically, say we have all of these cows, and then say we currently are at this I, all right? And since the biggest, obviously MA and MA2 are going to be 0, so this is a bad example. So let's say we're at this I then. Obviously, there's 2 cows currently on the graph that's bigger than it in size, and after sorting, this cow would have came first, this cow would have came second, and this cow would have been third. So by the time we got to this cow, MA, the latest cow that we already chose, would already be J, which is later than it. And MA2, the second biggest cow that we already chose, is going to be this I, which is also behind it. So if both MA and MA2 is behind the current I, we realize that we can't choose this I, because essentially we can only do one operation to adjust the sequence of A before we construct B, and we can't move both of them, because that would be required in order for us to choose I after already choosing those two. And since we can't do both these operations, we just have to skip this I. However, say we are currently at this I, which is really big. Let's just say it's not that tall actually. Let's just say it's like this size, all right? And notice that both the MA and the MA2, which in this case, this will be MA and this will be MA2, both of them are smaller than this I. And that means this I can be easily added to the end of all the numbers that we already chose because, well, it's greater than MA. And there's a third situation, in which case this pillar, oh shoot, this thing is in the middle of those two. So we wanted to choose this one. Well, then it's in the middle of MA and MA2. So then if we haven't already used our operation yet, we can just move the MA to the front of the sequence. And we actually have a specific place to move it, where we'll just move it in the front of this because that'll be the optimal one. Or we can just move it to the... actually, we can't move it to the front. My bad. If we move it to the front, then we might disrupt the order of the sequence. So we just move it somewhere between MA2 and I, because we know I is bigger than MA2. So after moving it we can choose this I because we know that I is, once again, the latest position that we're going to choose if we choose this I. So if I is between MA and MA2 and we haven't already moved, we would be able to choose I while using our opportunities to move the array A by 1, and this is demonstrated here. So first of all, obviously, if the position is greater than the latest we already chose, we can comfortably add it to the end of everything we chose. However, if it's in between MA2 and less than MA, well then we can use our opportunity to mark moved as 1, and then we renew MA by moving MA back to behind I's current position. However, you notice that if it's both less than MA and MA2, we can't do anything, and we just have to skip this I. And how do we know this is correct? How do we know we can always use this move on the first time that we see a contradiction? The first time that we saw an MA being greater than I, we move this J. How do we know this is correct? Well, this is actually a greedy approach because we know in lexicographical order, the first position that differs is what matters. So if we don't use this opportunity to move on the first MA we meet, any later position is not going to matter because we already had a less value when we face this J, as opposed to if we moved it. So this is how you do this problem. It's basically a greedy plus a simulation where all you have to keep track of is MA and MA2. And this is actually a very, very easy contest for USACO Silver, especially for February, especially for 2025 February. And this problem is not alone, as I'm going to be explaining in further videos. Both the other two problems are also very, very easy. As this one, just look at the length of the code. Like if you compare it to 2024 February, it's not on the same level, right? Target practice 2, test tubes, and movable are all like platinum difficulty. Okay, that's an exaggeration, but it's way more difficult than this thing. Okay, so I hope this video helped, and after this, you know how to solve the USACO 2025 February contest silver problem 1 of best lineup. Thank you for watching.